Welcome to the 0.2 Gram podcast, where we talk about fascinating diamond science. We're Janina and Karin, and we hope you will join us as we talk with many interesting diamond personalities.
Today, we're talking to Graham Pearson to learn about whether it will ever be truly possible to fingerprint diamonds from different mines. Graham is a professor of geochemistry at the University of Alberta in Canada. He's based in Edmonton, and this is truly the Great White North because it snows in July. So we're going to be talking to Graham today because he is a genius in analytical geochemistry. He developed the first technique that used sulfide inclusions to date diamonds, and he also developed the only technique that is currently capable of measuring trace elements in diamonds. We hope you enjoy this conversation that we had with Graham.
Hello, Graham, and welcome to the 0.2 Gram podcast. First, we would just like to know kind of like how you got there. Like, did you always want to do geology? Like, what drew you to geology at the start?
Hello, thanks for having me as your guest on 0.2 Gram. So I was always interested in science growing up, and the thing about geology is it's a great combination of sciences. So for people who are really interested in science but can't really decide which particular science they want to get into, geology offers a sort of almost unique combination of lots of different sciences that you apply in really quite unusual ways, to both together and independently. That, combined with the fact that it offers you the chance to see some of the most remote and amazing places on the planet, is a pretty nice combination, actually. So that's what attracted me.
So what are, like you mentioned, like a few remote places that you've been to. So what are, some of like the most spectacular places that you've done field work?
So diamonds are not 100% of my research effort, but in combination with looking at diamond deposits and looking at other rocks, then I've been to the extreme north and south ends of the planet. So up in the Canadian Arctic, I think we got to 82 degrees north before the helicopter blades started icing up and the pilot was urgently wanting to fly south again. And that's a pretty unique landscape that is really hard to replicate anywhere else. And so all over the Canadian Arctic, but also in places in Africa, really amazing places. In the African landscapes really varied. So,
and we all know it's the best continent. So
yes, that's right. So
Sure.
It's the best continent. No, Africa is a pretty amazing place, and so particularly from the diamond aspect, then there are many parts of Africa that you can visit. So I mean, from North Africa right down through to the southern tip of Africa, you can go hunting diamonds there and looking at diamond deposits. So yeah, and then Russia and Australia. So almost you can almost stick your finger on any part of the map, and there's always interesting rocks with or without diamonds that you can find an excuse to go visit as a geologist.
So Graham, you've also told us about some really interesting fieldwork that you've done in the Pacific. On some really cool Pacific islands, and you had a kind of a hairy story of where you were trapped in a hurricane during field work.
Yes, so we went looking at
typhoon.
No, hurricane. Great. So we went looking at volcanic rocks in Fiji, in the Fiji archipelago, on a little remote island, a grad student and I, and there was a grade 5 hurricane circling around that area of the Pacific, and it looked as though it was going to miss us. But unfortunately, it did a U-turn and came back and actually trashed the island that we'd been working on. And myself and the grad student managed to get off that island, but still I got hit by this grade 5 hurricane with my wife in a beachside cottage where you could hear this thing going on outside, ripping trees up, hurling trees over it, ripping the roofs off every other building. Our building had a roof tied down with steel cables, so that didn't happen. But there was seawater being driven through solid walls by 200-mile-an-hour winds. Yeah, that was pretty hair-raising.
So geoscience is an exciting field to get into. So, you get to
Yes.
see rocks, go to remote locations, experience hurricanes. So, if you like adrenaline, geology seems to be the place for you.
Yes, yeah.
It can be.
Yeah, that's right. It's kind of, you make your own luck or bad luck, and so it's up to you how much adrenaline you want. Yes.
So I guess you mentioned already that you're been to all these or some of these remote places to study diamonds. So why in particular, or were you interested in studying diamonds, and what is one of the most interesting aspects of diamonds to you?
So I got into diamond research almost through the back door, really, in that I had a PhD project on some diamond bearing rocks, but the project was about the rocks. And I mean, to be honest, I didn't really understand what the project was about that I was being offered, other than the supervisors were very excited about it and wanted me to do that project rather than the initial project I'd applied for. So I just said, well, okay, and that was on some very interesting rocks that actually had X diamonds in them. So pseudomorphs, pieces of graphite that used to be diamond that came up slowly enough in the earth that the diamond reverted to graphite. And so that project involved piecing together the solid evidence for why these aggregates of graphite. What was the critical evidence that enabled us to say that they used to be diamonds? And so that taught me a lot about diamonds and diamond crystallography and the sort of rocks that diamonds occur in. And so it all then sort of snowballed from there. And one of my advisors was very influential in the diamond world, Peter Nixon. And so he had a lot of really great contacts and a lot of amazing rocks to work on. And so it was actually then very easy, having gotten interested in diamonds, to continue doing diamond research.
Yeah, and so I guess that sort of emphasizes that, in life and in research, like, you don't always know where things are going to go, right? And you just sort of have to say yes along the way to opportunities that come up, and then somehow you end up where you need to be, because that's certainly sort of a path that happened with me as well. Like, I didn't plan to study diamonds. I knew that I was sort of generally interested in earth science, and went to go study that as an undergrad. And then after my honors year, I wasn't really sure what I wanted to do, but I applied for a few jobs in the Cape Town area. And then I ended up at Mineral Services applying for a job. And John Gurney, who's sort of a pioneer in the diamond field in South Africa, he offered me this research project. And at the time, I was really keen to travel because I was still really young. And he pretty much just met me. And in that meeting, he was like, well, we have these diamonds in the safe and we need someone to work on them. We haven't been able to find anyone. You'll get to go to DC to do your lab work. We'll pay for everything. And we'll also enroll you as a master's student or a PhD student at UCT, and we'll pay for your fees as well. Are you interested? And I was like, yeah, I'm interested. It's just sort of like, he just sort of handed it to me like on a plate. And so it wasn't like I'd ever sort of thought that, diamonds are where I want to be. It just sort of happened that way. And I just said yes, because it was what I needed at the time. And then as it turned out, like when I graduated, at my graduation ceremony, John Gurney actually told my dad that I came around at the right time for him, because he was looking for someone to do this project because he had the diamonds in the safe for, I think, a year or two, and he was looking for someone to work on this project. And so it was just sort of strange to hear that perspective, because for me, like, he came around at the right time for me. And then he was like, no, I came around at the right time for him, because this project, I guess, just the timing just sort of worked out well. And so it isn't something that, you can necessarily plan. You just sort of, go with the flow in life, and then things tend to work out sometimes.
Yeah, I think I think a lot of us don't really have a plan, or if we had a plan, it didn't work out. So my plan, if I had one, was to be a mining geologist. That's why I went to the Royal School of Mines at Imperial College. And after about a year, I got interested instead in igneous petrology and geochemistry, and ended up doing research. And then I thought, well, I actually applied for several PhDs, one at Oxford, which I didn't get, which actually worked out to be a great blessing, because I couldn't have done better with the project that I ended up getting, which, as I said, I didn't really understand what it was, but it worked out to be an amazing project. So, and actually at the same time, I had this, I was offered a job in a South African coal mine by Anglo-American, so I had to choose between that and doing this PhD. And I guess both of them involved carbon, but one was a nicer form of carbon than the other. So.
Well, I'm glad you didn't choose the coal mine, because that would have...
Yeah, I know, that wouldn't have worked out too. Yeah, I'm kind of glad. But I mean, I was sort of this close to taking that.
Oh.
Yeah, I think most geologists actually kind of don't go into earth sciences or geology at the start. At least that's the case for most of my friends from my undergraduate degree. Most of them did something else beforehand, because I feel like in most schools you're not taught earth sciences or geology. It might be like a one original course, or like a section in like geography. At least that was for me, but it wasn't a subject, and most people don't even know about it. And to this day, when I tell people I'm a geologist, they mostly ask, "Oh, you study rocks? Like rocks? Like you look at them?" So
yeah.
That is.
I have my pet rock collection. That's what a geologist does.
Yes.
Okay, so Graham, let's start with some diamond basics. So diamonds are pure carbon. So as you mentioned, same as graphite, just a nicer, better looking form of carbon. So carbon, well, diamond is relatively pure. So it's like 99% carbon, right? And so it has only a very few impurities. The most common impurity is nitrogen, and even that is in the hundreds of ppm range. So, the second most abundant element in diamond is still a trace element. And so what are the main things that we can actually measure in a diamond that can actually tell us anything about how the diamond formed, where it formed? So, what are the main characteristics that we set about to measure in diamonds that can tell us something useful?
Well, for the longest time, people couldn't measure anything in diamond because it was just carbon. And then when isotope geochemistry came along, then diamond was one of the first things that was analyzed for its carbon isotopes, because there was this huge interest in where the carbon in diamonds comes from. And so some early measurements were made, and so there you're essentially measuring the ratios of the abundances of the two common carbon isotopes, carbon-12 and carbon-13. And so while that was an extremely powerful thing to do in terms of that was one of the first indications that told us that diamonds essentially come from the Earth's mantle. There's some complications to that story, but that was the initial result. But of course, you're only measuring two things there, and so there's a range. It turns out there's actually a bigger range than we thought there would be in carbon isotopes. But you're really only measuring one parameter, the carbon isotope ratio. So then, many years later, when mass spectrometers became more sensitive, that gave us the ability to measure the isotopes of nitrogen. So you're then measuring the relative abundances of nitrogen 14 and 15. And again, that actually showed that there's a range in nitrogen isotopic compositions, actually quite a bit more than we thought there would be. But again, you're just measuring this one parameter, the nitrogen isotope ratio, and you're measuring the carbon isotope ratio. And so that potentially gives you a 2-parameter space to explore. And that offers you some power in trying to work out what the sources of carbon were. So did diamonds just form from carbon that's always been in the mantle since the Earth was accreted, or did diamonds form from the recycling of crustal carbon, or a combination of the two? So those methods have been very powerful in answering those questions. But because there's still relatively limited variability between the different diamond suites. They are not as powerful in terms of trying to distinguish between different diamond deposits. There are some diamond deposits where specific types of diamonds from a specific deposit have much more unusual carbon isotopes, for instance, than other mines. But that's sort of unusual. And actually, if you took random samples of diamonds from around the world, there's a very high probability that you would come up with a carbon isotope ratio that would be very close to a value of -5 per mil. Very high probability. And so that doesn't give you a lot of options in terms of discriminating, say, geographic source. And you can combine that with measuring the nitrogen abundance. And sure, there are a few mines that have unusually high nitrogen abundances, but by and large, the nitrogen abundance in diamonds from any given mine varies a lot, and it seems to vary in a non-systematic way. So again, you've got this limited parameter space to explore. So really, I mean, those methods have been great for telling us in general about the sources of fluids that make diamonds, and they've been very good, especially looking at the nitrogen contents and the way that nitrogen atoms aggregate through with temperature and time in diamonds. That's been very useful in telling us about the time temperature history, the residence history of diamonds in the mantle. But even all those methods combined are of relatively limited use in telling you where a particular diamond comes from.
So are there, like you mentioned that by and large, if you take diamonds from different localities, different deposits, by and large, there's going to be a large overlap between the compositions of those diamonds. Like the carbon is going to be fairly similar because we're really distinguishing between sort of mantle carbon and crustal carbon, not between different geographic locations. And then also like the nitrogen content is very variable. And so most localities, you know, they don't really sit apart from each other. You know, there may be some deposits that we know that have extreme compositions. For example, Jericho has, you know, like the -41 per mole carbon. And we know that Argyle has, you know, certain nitrogen characteristics in terms of the aggregation state. But, you know, sort of like those are just like sort of two extreme examples I could think of. But in general, you know, just to emphasize that most localities globally, right, have a lot of overlap. So you can't really use nitrogen and carbon really as any sort of distinguishing characteristic of geographic location.
Yeah, I think that's a good way of summarizing it. That there's very limited power really in carbon and nitrogen isotopes in particular to give you a geographic tracing. Yeah.
Well, so this whole variation also is not just like between different continents or different like larger areas or cratons where the diamonds come from, but also between like smaller, even like maybe on the kimberlite or mine scale and the country scale, we don't see a large variation between the carbon isotopes, the nitrogen isotopes. They all still overlap. So is that?
Yeah, even within even at a particular deposit, you could have some diamonds that have mantle carbon, some diamonds that have crustal carbon, and also a wide range of nitrogen. So even at a very, very local scale, from a single deposit, you could have a wide range of characteristics that overlap with each other. And so this is, I guess, one of the challenges with doing diamond fingerprinting is because what do you then really use when carbon and nitrogen really just overlap with each other globally? There's no real distinguishing characteristics.
It's both the overlapping, but it's also the case that you get there's a very high probability of getting the same value for carbon isotopes or nitrogen isotopes, but we'll take carbon isotopes because it's much more of a routine measurement. That if you analyze the carbon isotopes in a diamond from any one country or between two different countries, there's a very high probability of getting exactly the same value from one country or one mine and another. And so if you turn that around in a statistical sense, the question that you would want to ask is, what is the probability that this diamond came from a particular deposit? And your power, the resolving power to answer that question is very, very low with carbon isotopes, because in many places there's a very high probability of getting exactly the same value for the different mines. So while there is this big range, actually much larger range in carbon isotopes than most people ever thought there would be, so the values would range. They're on a per mil scale, so the change you're looking at sounds small, but actually in terms of our ability to make the analysis, it's pretty big. So the range is, the value is a per mil, or a 1 part in 1,000 difference. And the range is the extreme range is from minus 40 per mil to something like plus 5 per mil. So a plus 45 per mil range. And our precision on that measurement is 0.1 per mil. So the range is very large compared to the precision. Nonetheless, most diamonds have this canonical mantle value of -5. So if you just had to randomly guess, if someone gave you a diamond and said, guess what the carbon isotope composition of that diamond is, if you were sensible, you would put a lot of money. If they gave you a lot of money to put on it, you would put a lot of money on that value being -5, or within 1 per mil of -5. So that doesn't give you a lot of resolving power in terms of being able to answer the question, what is the probability that this diamond came from a particular mine?
Yeah, so it really is a challenge. And so this is where trace elements comes in. And I guess this is really why, apart from your very interesting diamond geology background and all your numerous achievements, the reason we wanted to specifically talk to you today was to cover sort of trace elements in diamonds. And so could you just explain a bit about, why we are interested in measuring trace elements in diamonds? And, potentially it's become obvious, through our discussion now with the carbon and the nitrogen, and how there's no real resolving power between different locations. Explain to us why we are now interested in measuring trace elements in diamonds.
So the trace elements give you a much greater dimensionality to the data. So with carbon and nitrogen, then you've got relatively little dimensionality to the data. With trace elements, you can measure easily 30 or more different trace elements. And those trace elements all have different geochemical properties. And so, and those different geochemical properties cause the trace elements to vary in different ways, depending on which geological process is operating during diamond formation, or has operated to make the source for the diamond forming fluids. So because you've got many, many more elements to look at, and some of those elements have their own isotopes that you can measure that are either radiogenic isotopes or stable isotopes, but particularly, say, strontium isotopes, lead, and neodymium and hafnium isotopes, they're frequently measured in rocks, and it opened up the possibility of also measuring isotope ratios like that in the fluids in diamonds, which is essentially what you're measuring when you're measuring for trace elements anyway. For the carbon, you're measuring the actual structural constituent of the diamond. But in the trace elements, we think we're mostly measuring minute amounts of fluids trapped in the diamonds. But the great thing about that is that those fluids have a huge variety of different elements. The challenge is actually measuring those elements, because, as we've said earlier, that the carbon in diamonds is very pure, and so there's very little of those trace elements around. But still, it's this attraction of being able to access 30 or more elements and the information they give you that makes it attractive to look at the trace elements in diamonds.
You already mentioned that it's challenging to analyze these trace elements because they're in trace amounts, so they're really, really minute amounts of these elements within the diamonds. But obviously that's very difficult. But we can measure trace elements of really small amounts in other elements, in other minerals. Like, why is it so difficult for diamonds in particular? What makes it so hard?
There are lots of reasons why this is a big challenge in diamonds. So one is that diamond's an incredibly robust material. So that means that it's not easily dissolved in standard lab reagents. So for some of those other elements, some of those other minerals where we analyze trace elements, you can drop them in hydrofluoric acid, and within a few hours they'll dissolve, and then you can analyze those solutions very simply for trace elements. With diamonds, you can't do that. You have to have extremely specialized reagents to dissolve them in, and those reagents often are so impure in trace elements themselves that you're then never really sure whether you're analyzing the trace element composition of the diamond or the nasty reagent that you needed to dissolve the diamond. Then a second issue is that in most normal minerals actually have, compared to today's extremely sensitive analytical instruments, most normal minerals have quite a lot of so-called trace elements. So we're talking about parts per million, but that doesn't sound very much, but that's well within the capabilities of modern instrumentation to measure parts per million level impurities. That's regarded as routine these days. Now, the problem with diamond is that the trace impurities that we're interested in, these so-called trace elements, are what might be called ultra trace elements. They're present at part per billion, 1 part in 10 to the minus 9, or part per trillion, 1 part in 10 to the minus 12 levels, or even less, in parts per quadrillion, 1 part in 10 to the minus 15. And so once you get to those levels, you've not got many atoms to play with. And so your signal is not very big. And then one of the other major challenges as well is that there's simply no analytical standards. So actually for a lot of minerals, you can either synthesize a mineral, dope it with known amounts of trace elements, and use that as an analytical standard, because you need that to calibrate your instrument, but you also need another standard or reference material to check that you're getting the right result. And we can do that easily for other minerals. We can either make them synthetically, or there's plenty of them around with high enough abundances of other elements that are they're uniform in composition, that we can select and generate our own reference materials. No diamond standard or reference material exists for a trace element measurement that's in common circulation, that everybody agrees on a value with. And so those are some of the big reasons why it's particularly difficult to analyze trace elements in diamonds. So while it sounds like a great thing to do, and it is, and people have thought about doing this for many years. In fact, people started doing this probably in the mid to late 70s. One approach then was a technique called induced neutron activation analysis, where they put the diamond in a nuclear reactor. And that had the rather big drawback that the diamonds turned black when you did that. And so it wasn't a very good way to go if you wanted to preserve some of the diamond in its original state. But nonetheless, it generated some of the first data that showed that this would be an interesting thing to do, and that there were actually measurable abundances of quite a lot of different elements in diamonds.
Your lab right now in Alberta is pretty well set up for measuring trace elements in diamonds, and it's becoming almost a routine measurement. It's still a challenging measurement, but nevertheless, you have it set up so that, if you wanted to come spend the time in the lab, you can spend a few weeks or a few months there and measure these trace elements. So can you talk us through how you developed this technique so that it has sort of become semi-routine, even though there aren't a lot of data for diamond trace elements yet? But I mean, you started working on this much more than a decade ago. And so can you talk us through just how you came up with the idea for the technique that you're using now, and talk through some of the developmental challenges that you faced in getting to where you are now?
I think one useful adage in science is that if something's easy, then someone's almost certainly done it by now. And so whilst this idea of analysing trace elements in diamonds, lots of people, I'm sure, had the idea, one of the reasons that there was very little to no quantifiable data in the literature is because it's not easy. In fact, it's the exact opposite of that. It's very, very difficult. And so I think I had the desire and the drive to analyze trace elements in diamonds for a long time, but it took a while to think about how to actually go about that in a new way that was actually going to produce better data. And So because of some of those analytical challenges that we just thought about, then one of the things that became clear is that we had to develop a method that didn't rely on having a known, well-characterized diamond standard, because if you like, it's almost a tautology in that if you need a reference material to have the method. You can't have the method without a reference material because you don't know whether you're getting the right answer. And so I came to the realization that really the best way around that was just to sidestep the whole thing about having a diamond standard. And the way to do that would be to get rid of most of the carbon atoms by ablating them with a laser. And so a high energy laser would essentially vaporize the carbon as CO2, and all that you're left with are these ultra trace elements, which most of which are actually not very volatile, and so they remain in the residue that's left. And you take those up into solution, and so that you've then got a liquid solution that you can analyze against a calibration solution that's almost perfectly matrix matched, because there's no carbon matrix in your solution, and you can make a reference solution that's also got no carbon matrix. So that neatly sidestepped, so that idea neatly sidestepped the fact that there was no analytical standard available. The challenge, so that sounds all very well, and okay, that's easy, but then the challenge is, all right, how do we do that? Because you've got to do that in an ultra clean environment to make sure, and this is the same with any ultra trace element measurement, the biggest challenge is, because the elements are there at such low levels, is to make sure that what you're analyzing is actually what's in the object that you're analyzing, and you're not analyzing environmental background. This was really the same challenge when people were trying to constrain what the ill effects were on having lead in petrol. For those of us that are old enough, you guys aren't, to remember lead, we used to put lead in petrol.
I remember.
Yeah, actually, some countries did it for a long time after a lot of countries banned it. But it was the same challenge. I mean, people knew that lead ought to be getting into the environment from lead in petrol, but because the natural environment and even lab environments are just swimming in lead pollution, it took years for people to develop adequate methodologies that gave them confidence that what they were measuring were trace amounts of lead derived from gasoline pollution and not derived from atmospheric dust or mining or whatever. Yeah. And that was done by geologists, by geochemists, actually, who led the way in solving that issue. And it's the same issue with diamonds. So you've got to have a method where you're confident that what you're analyzing is a trace signal that comes from the diamond and not from your lab or even from you and your lab coat. That then led to this concept of doing it in a closed cell environment. So you don't just stick the diamond under there and ablate the diamond. You've got to do that with an ultra clean little mini environment that you put the diamond in a little cell. Yeah, so we have this ultra clean Teflon cell with a fused silica glass window, and so that we got to that stage by my lab manager and I, Jeff Knoll in Durham, and I iterating designs where you need to ablate the diamond but trap the material that comes off during that vaporization process so that you can add acid and recover them. So after a few iterations, we came up with this closed cell design. So it has Teflon that you can soak in very aggressive acids to leach out all the trace impurities in the Teflon.
Yeah.
And it has a fused silica glass window. And that in the end was probably our biggest challenge in cleaning the fused silica glass windows, because you get a lot of impurities from those during the polishing process involved in polishing the glass. So that took actually a long time to get to the stage where we were confident that we weren't getting wholesale contamination from the fused silica glass window. And so that gives us A, the ability to ablate the diamond, and B, the ability to track the product. And that's in many ways an improvement on what people were trying at the same time, which was to directly laser ablate a diamond and send the product into a mass spectrometer straight away. And while that will work for quite impure diamonds to some extent anyway, where the diamonds have got probably 2, 3, 4 orders of magnitude higher concentrations than these ultra pure, beautiful gems that are the valuable forms of diamond.
Yeah.
The problem with that method is still that there is no accepted diamond standard. And so you really don't know whether the values you're getting are benchmarked at correct values. That's one of its biggest weaknesses. And then the other is that the detection limits, so the confidence you have that what you're measuring is a real signal or just background signal, the detection limits for that method are really not too good, and they're fundamentally limited by the amount of energy that you can put into one package of photons that goes to ablate that diamond. And so the other beauty of and the driver for why we wanted to come up with this closed cell approach is because you have complete control over the detection limits, the signal to noise ratio. So if you want more signal, then you just ablate for longer, and all you're doing is adding more photons, and photons don't contain any trace elements. So actually you're getting a bigger signal at really pretty much the same blank or background level, because the thing's done in a closed cell environment. So that gives you much more flexibility. You can ablate for as long as you like to get enough analyte to measure, because what we can see now is that with very pure gem diamonds, even the abundance of trace elements in those still varies hugely, and you never quite know what you're going to get when you ablate one diamond versus another. The abundances can vary by 2 or 3 orders of magnitude, even within similar looking diamonds.
Okay, so I want to go back a bit to get some more details about sort of, if you can say, like, which year you started with the first sort of ablations, where you first came up with a closed cell, like all the shitty data that you got first, and sort of when did you know that this could be a successful technique? Because there was obviously a lot of trial and error in the beginning when you were still sort of fine-tuning the design of the ablation cells, and then also maybe potentially testing out different lasers to see which ones would be the most successful. Because you mentioned you're using a high energy laser. Can you just talk a bit more about, what the wavelength of that laser is, what the energies are? I know in Alberta you're using a 193 argon fluoride excimer laser. Like, was that the same laser you were using in Durham? So if you could just talk a bit more about, sort of those details about deciding on which laser to use, and then also, some of the frustrations, that went along with all the trial and error that must have come along with trying to develop this.
Well, so I think my philosophy is that if Einstein, I think, coined the phrase that research is 99% perspiration and 1% inspiration. So if Einstein finds the process of research 99% perspiration, the rest of us have to work pretty damn hard. And so having had that idea, you need, the concept was good. My lab manager and I, Jeff, we played around with just seeing if we could get an ablation to work. And having established that it was possible, you're then faced with the realization that something being possible is one thing, but proving it to be a workable method is another. And so we then realized that we needed a PhD student to take that through and prove the concept. And so we were lucky enough to get some initial funding from the Diamond Trading Company that was part of De Beers. And we took on a student, John McNeil, who was a very patient Irishman who had just the right sort of attitude to do this, because it did require a huge amount of effort, patience, and replication. So one of the first things John did was just to run 30 or 40 background measurements, blanks, which doesn't sound very difficult, but it actually is in this clean environment. Several weeks analyzing essentially nothing, no sample data, you're not getting interesting data, you're just measuring the background. And not every student wants to do a project where you're just measuring background contamination for maybe a month or two on end. But that was what was necessary, A, to prove that we had a clean enough lab to make the measurements, and then to start ablating the diamond to make sure that we can ablate the diamond in a controlled and nice manner, because some of the approaches that were being used to directly ablate diamond at the time and send the signal into the mass spectrometer were producing, in terms of geometry, really very awful ablation pits in diamonds. They're very irregular. The diamond would be cracking, and there'd be a lot of buildup on the diamond surface of ablation products. So we started using a 213 nanometer laser, which works surprisingly well. Diamond absorbs that wavelength energy pretty well, and John showed that he could produce really very geometrically nice pits. And you want those pits, well, they're particularly important for direct ablation because you don't want to fractionate one element from another by having poor pit geometry. It's not so important actually with the closed cell ablation, but you still want to know where you've ablated quite precisely. And so having good pit geometry is very important from that point of view. And so the 213 worked pretty well, but that laser was of limited fluence. So the fluence is the energy density of the laser signal or the laser beam. And at low fluence, you're not excavating or vaporizing diamond very rapidly. So we needed a higher fluence laser. Nonetheless, a lot of the initial work done by John was done on this 213 laser. It took a long time, hours and hours, to ablate a diamond, and John produced some very interesting initial data. I mean, the next step along the way was to demonstrate that we weren't vaporizing and losing a lot of trace elements. And so we did some experiments where we took pieces of diamond and we combusted them in sealed platinum jackets and leached the inside of those specifically for lead and rubidium, two of the most abundant of the volatile elements. And we then compared our offline ablation measurements to those total combustion measurements, and we got pretty good agreement. So that convinced us that we weren't losing wholesale rubidium and lead in the ablation process. And that was about right. That intuitively should have been correct because this is a closed system. And so even though you are vaporizing some of those elements more than others at the ablation site, they shouldn't go anywhere in a closed system. But that all took time. And so probably it was only really maybe 2 to 3 years into John's PhD project where it was clear that we could produce very reliable, good, accurate data. And then at that stage, moving to Canada gave us the opportunity to get a higher fluence laser so that we could ablate diamonds more quickly and more efficiently and probably more accurately in a spatial context. We just developed a much more sophisticated laser setup that was much more, well, it was a bespoke setup specifically designed to do this. The one that we used in Durham, we actually just sort of jerry-rigged to do the job. It was never specifically designed to do this. So the system we have now is bespoke and is specifically designed just for ablating diamonds. But I'd say, yeah, it's taken a process of over 10 years to get to the stage where this is anything like routine. And it's only routine because we've got the setup to do it. It's not routine in the sense that you could go to anybody's geochemistry lab and do this because they're not usually set up to analyze diamonds, specifically with this type of laser setup.
Yeah, so I'll just emphasize then that, your lab is the only lab in the world that is doing these measurements. And so, yes, it's routine in your lab, but, no other lab in the world is currently set up to do these analyses. And so I know, there's one or two other people that, are interested in setting it up, but, setting up any new technique in a lab, even if it's been set up in another lab, you still have to go through the process in your own lab of proving, that you have low enough blanks and that you can do the ablations properly and make sure that you have the correct laser settings. And so even that process, after it's been established somewhere else, if you want to set it up in a new lab, even that's going to take a number of years. And so I like how you emphasize that, John McNeil was a very patient man who, for 2 or 3 years was, just trying to, prove that this technique could work without actually having any sort of data yet, and so it was really just, setting up the technique and deciding how best to go about it. So, science is a process.
It's also, I think when you develop a method, though, you to my mind anyway, you never really want to be the only lab doing this sort of thing because you're sort of working on your own and really developing a method, you do so with the idea that lots of people will be able to do this. And there are labs now that are well on the way to being able to make the same sort of measurements, or maybe even to be able to do it better than we can ultimately. And that's great. That's how science.
Yeah, that's what you want. Yeah.
Well, it does help to compare between different labs as well to sort of better establish the method and then also better confirm your results.
Yeah, that's right. I think any robust analytical process, if you have any sort of claim to it being routine, it has to be reproducible between one lab and another. Yeah, and it's really, again, that gets back to why you never really want to be the only lab producing data, because nobody else can verify your data. That's not a good place to be scientifically for a long period of time.
Yeah, absolutely. And so I think ideally you'd want maybe in the future, similar to what they have, for the Earth Time Initiative for, UPV dating, where they have, a set of standards that they can send to different labs to test the precision and accuracy that is possible with their specific instrumentation. I think potentially in the future, it would be nice to have, a set of a few diamonds that can be sort of traveling standards that people can measure in different labs once they have the technique set up, just to prove that, that we are reproducible to each other.
That's right. I think that's really ultimately where one longer term goal would be, to have a diamond standard, even if it was a synthetic diamond doped with even a relatively small number of elements. That would be extremely useful to be able to, especially if it was possible to make the trace element distribution in those diamonds as homogeneous as possible. We have we made some comparisons between our lab and direct ablation labs where we can clearly reproduce the patterns of the trace elements, the inter-element fractionation. What's much more difficult to reproduce is the absolute abundances, because we're using completely different calibration methods, but also we're analyzing different parts of the diamond. And in the diamonds that are high enough in trace elements to actually make a measurement by direct ablation, then these are diamonds that are absolutely full of fluid inclusions that are distributed in a fairly inhomogeneous way. And so there are significant differences between one part of a diamond and another. So that you can't use as a long-term, really high quality reference material.
Yeah, and I think that potentially links to the fact that, you mentioned earlier that the trace elements are incorporated in sort of micro to nano fluids within the diamond. It's not actually, the trace elements we don't think are incorporated into the diamond lattice itself. And so it's not a uniform distribution, right? So it's, if these are trapped in microfluids, that really just enhances the fact that there's a heterogeneous distribution of these trace elements throughout the diamond. And then that is, as you said, part of the challenge of proving reproducibility, because you have to, ablate at the same place where you have the same concentration of whatever you're trying to measure.
That's right. So the first person to image one of those fluid inclusion heterogeneities in a diamond was Oded Navon in Israel. And I believe it took Oded and his student years to actually find a single inclusion that they could image and point to and say that's where the fluids are in those diamonds. Yeah.
In the gem quality ones.
In the gem diamond, that's right. Yeah. In the fluid rich diamonds, I think Oded was one of the first people to image those properly as well. And there are millions and millions of those fluid inclusions. But then when you transfer to gem quality diamonds, it's extremely challenging to find anything visible to tie your measurement to.
I guess one of the neat things too with analyzing, like assuming that what we measure as the trace elements is from these micro or nano inclusions, is that we assume that these fluid inclusions, or so-called fluid inclusions, are the fluid that originally formed the diamond. So that's what sort of went through the earth mantle and then crystallized. From that is what the diamond crystallized. So I think it's very good that we now can have trace elements of the diamond forming fluid, whereas even in like the gem quality diamonds, and then we could compare the not so pretty diamonds to the prettier gem quality ones.
Yeah, I mean,
which is what most people are interested in.
Yeah, yeah, and I mean, this gets back to the issue also of what you're analyzing. So you with the gem diamonds, you want to be absolutely sure that you're not analyzing late stage cracks where external sources of fluids, when the diamond's been in the crust, have crept into those cracks. And so, yeah, you tend to choose these pristine looking gems that literally have nothing in them, or at least nothing at the above a few parts per trillion level elemental impurities that's not nitrogen or carbon.
Yeah, so just like to make a corny sort of metaphor, or sort of, yeah, like you have gem quality diamonds that I guess most of, the public sort of think that those are the most desirable because they're the most pure diamonds. But from a scientific point of view, actually, like the diamonds that have the least amount of impurities actually tell us the least, so they have, very little personality. And, like the diamonds with impurities and inclusions that have some personality to them, they can tell us some things, and they can teach us about the earth. And so from a scientific point of view, I mean, I've always preferred diamonds with inclusions and some character to them, like colorful diamonds with inclusions, or like, the sweeter diamonds I studied from Zimbabwe, with lots of graphite in them. There's different kinds of beauty, and you don't just need the most flawless, most pristine, purest diamond, because what is it really going to tell you, So I prefer, the ones with all the flaws and imperfections and, got some character and personality to them.
Yeah, no, that's right. You want a signal to measure, and you want a scientific story to tell, and that's very difficult to get out of very high quality gems. It's now becoming more and more possible. I mean, in fact, I mean, an interesting thing about doing the ultra trace measurements is that it does verify in many ways the extreme purity of these highly valuable ultra pure gem diamonds. But it, as you said, it really limits the amount of scientific information that you can get out of them as well.
Yeah, for sure. And so how many suites of diamonds have now been analyzed sort of for their trace elements? How much of this work has now been done? You've been in Alberta for around 10 years now, I guess, maybe less, 9 years, 10 years. But like how many suites of diamonds have now been analyzed for their trace elements, and what have we learned from these studies?
Well, in short, not very many, and that's not because we haven't been doing anything. That's just a reflection of just how difficult the studies are to do, and also the fact that you want to perform these studies on well-characterized diamond suites from known locations, where you're not just picking random diamonds from places that you're not really sure where they're from. So we've managed to do a number of studies now from various places in Africa. I mean, in terms of actual significant numbers of diamonds from specific locations, still there's a relatively small number of places that have been analysed. But that includes suites from Canada, and then you've analysed some diamonds from West Africa as well. But the door's open to do a lot more of this type of work on well-characterized specific diamond suites that also have a good scientific question to answer as well. And so going forward, it's really, well, what sort of scientific questions do you want to answer with this type of analysis? Because that has to be the driving force. And so really a fundamental thing that thankfully we have managed to establish is Oded Nevon in Israel has done a great job in showing from a major element perspective that the fluids that make the ultra pure, highly economic gem diamonds appear to be the same fluids that make the non-gem diamonds. And while that doesn't sound particularly exciting, it is scientifically, because it's very important to understand whether you're dealing with the same populations of diamonds, and actually you can use the non-gem diamonds in many more ways than you can the gem diamonds. So they give you much more flexibility to then answer other scientific questions. Yeah. And we've managed to now show the same thing from a trace element perspective very clearly, that where the trace elements appear to be reflecting fluid inclusions in the diamonds, it's very clear that those are the same fluids that are in the gem diamonds as are in the non-gem diamonds. And so that has been a good breakthrough that again increases the value of the data we produce. So then beyond that, really then we are interested in producing data that tell us, okay, where do the sources of fluids come from that make diamonds? And you can go back to the carbon and nitrogen measurements, and they give you some information on that, but you can actually get different information from the trace elements and in particular the isotope measurements that come with the trace elements, because we can measure these so-called radiogenic isotopes of the trace elements of strontium, neodymium, and lead, and they give you a time-integrated view of the evolution of the source of those fluids in different parts of the mantle. And it's very clear that there are a number of sources that are supplying fluids of one type or another to make these diamonds, and those sources vary in age, and they vary in the sort of geological processes that have made those sources. So it's really assessing the relative roles of fluids coming from the deepest parts of the earth. The diamonds are formed under continental roots. Those continental roots extend down into the mobile mantle as solid masses to a couple of 100 kilometers. And it looks as though the information we're getting from the trace elements and from the fluids shows that there's a component of the fluids that make diamonds that comes directly from way beneath those roots and is entering the root from below. But there are also components of fluids that are being derived from within the root that have been sat there for billions of years, and they are also being triggered into supplying components to those fluids in the diamond forming event. And so we're only starting to understand the interplay between those two sources, how those sources of fluids get to the state where they can make diamond forming fluids.
Yeah, and so I think you've touched on an important point, that we have lots of different environments where diamonds can form in the earth. We have so-called, like the shallow diamonds in the cratonic lithosphere, and then we have super deep or sublithospheric diamonds that form much deeper, around 400 to 700 kilometers deep. And even at those great depths, even there are different diamond forming environments. We have the boron bearing diamonds, the metallic diamonds, the carbonatitic diamonds. And so I think by analyzing trace elements in all these different suites of diamonds from these different from different localities, we have a better understanding of the deep carbon cycle and how, because diamonds are, the pristine sample to look at the deep carbon cycle and how carbon bearing fluids sort of flow through the deep earth. And so analyzing trace elements in diamonds, I think, is sort of a key thing or a key constraint to help us understand recycling of carbon fluids into the deep earth.
Yes, that's right. And I think particularly because of the interest in the super deep diamonds that come, the sublithospheric diamonds that come from much deeper than a couple of 100 kilometers. Yeah, it's going to be a key tool to unravel how those diamonds are made, what the source inputs are to those diamonds. That's right.
I think in this context, it's also important to mention that diamonds and the inclusions within those from those depths, like the super deep ones, are really the only physical, like pristine, as Karin said, geological sample that we can get. Like we have some like volcanic rocks that come to the surface that probably were at these depths, but they've been altered subsequently. So they can't tell us the full, well, diamonds can tell us more of the full story than these volcanic rocks.
Yeah,
we can.
That's the great thing about diamonds, is that they don't change en route to the surface, unlike a melt fluid. That even if you could say that one of these melts or fluids comes from 700 kilometers deep, it continually evolves in its composition towards the surface. And so what you see at the surface not the same as what you had at depth. That's not the case with diamond yet. What you see at the surface is what you had at depth, which makes them uniquely powerful in telling us what the deep earth is comprised of.
Yeah, and so I guess here I just want to emphasize the deepest that humans have been able to draw into they've only been able to draw into the crust, like 30 or 40 kilometers. That's like the Kolar draw holes in Russia. Diamonds are coming from at least twice those depths, the cratonic diamonds, and then like the super deep diamonds coming from even deeper. And so these are coming from places that are inaccessible in any other way but through diamond mining. And so if it wasn't for diamond mining, scientists would actually lose access to direct samples, from the deep earth that we can use to study our planet. The only other way to understand the mineralogy and the properties is either, through seismic properties or through doing high pressure experiments where we mimic these conditions. But diamonds are the direct pristine samples from the deep earth.
Yes, no, that's exactly right. Even with seismology has really been a very powerful technique for illuminating the interior of the Earth. But it's a signal that you're measuring. It's not a real sample of what's inside the Earth at great depth. Yeah, and that's what diamond gives you. It gives you the ability to reference those measurements that you make with techniques like seismology to a real thing you can hold in your hand that comes from 600-700 kilometers deep.
So to shift gears a little bit, or to go back to the analytical part of it. So if I was someone who's interested in going to your lab and analyzing some diamonds, what steps would I have to take? Like, walk us through from, like you said, it's a closed cell ablation. So I go there, like how long does that take? And then is it done with that? And can I then just take whatever I ablated directly to the instrument and analyze it, or are there more steps?
Yeah. So yes, it's quite a bit more complicated than that, and actually, the process starts out with just a fairly mundane process, which is cleaning the closed cells. So again, we have to be sure that what we're measuring, the signal we're measuring, comes from the diamond and not background contamination. So the first thing you do is to spend a very long time acid leaching all the contaminants from the cells and the windows that have been used before from other measurements to make sure that the signal from those measurements is all gone. And that can take a period of weeks to be confident that you've then got a set of these cells that are clean enough to measure. And then having done that, then you would check the contamination in those cells before you started measuring, and then having verified that the blanks that you get from that are okay and are suitable, then you can start ablating samples. And then it depends on the nature of the samples you have. So if you have samples that have got a lot of fluids in them, then you don't need particularly long ablation times, maybe an hour or so. If you have ultra pure diamonds, then you might need many hours of ablation to excavate enough material to make an analysis. Having done that, then there's some manipulation of the solutions that, well, you ablate the diamond, you take up the ablation product in a solution that you leach on a hot plate for some time, and then there's a few manipulations you have to do to get the sample into the right dilution. You have to add some internal standard to the solution before you take it to the mass spectrometer. And then you don't just put this solution on any old mass spectrometer. We have a mass spectrometer that's dedicated to only analyzing diamonds, very low abundance trace elements in diamonds. That's a luxury to have. A lot of mass spectrometers in industry labs have to analyze everything that's given to them, and then the abundances of trace elements in the materials that are analyzed might vary by 6 to 10 orders of magnitude. And so it then becomes very difficult to make measurements at an ultra trace level on a mass spectrometer that the week before was analyzing material that had 1 million to 1 trillion times higher concentrations of elements in it. So we have this dedicated instrument that only ever measures very low abundance trace elements. It never sees high abundance samples. It always gets cleaned out. and recalibrated before each run, and then you make the measurements, and then you check your data, and
Yeah.
that's part of the process too, is to verify that the analysis has been done correctly and that the data look okay, that there's no spikes in the analyses and no problems. And you might have to go back and repeat some analyses. So it's a lot of hard work. Yeah, it's not something that you do, that you turn up in the lab. There are methods for other minerals that you can turn up in the lab and get a couple of hundred analyses of trace elements in a garnet in an afternoon. This is
great.
analysis. Yeah. So you
That's
have to have
a
a
lot,
certain mentality to do this work. Yeah.
Yeah, and so just to give context, like I went to Graham's lab to do some trace elements in diamonds from Zimbabwe, and I think I had like 5 diamonds, but I did multiple analyses in each. And I was there for 3 weeks doing those analyses, but even those 3 weeks were, I feel, too short because I was working around the clock and I was very stressed. And I needed a lot of help in order to get everything done. So I had to rely a lot on other people to, do the blanks for me ahead of time and clean the diamonds for me ahead of time before I showed up. I mean, it is, if you come as a visitor, then, you do need to rely on other people a lot to help you out and to have success in the lab. And 3 weeks, I think, is just too short. But, not everyone has the luxury to come for like 2-3 months and do these analyses, properly at their leisure with no help at all. It helps that your lab is really well set up and has good support staff, and Sarah runs it like excellently. I think because you have that great setup, I think it is possible for visitors to come, but knowing that it's going to be an extensive campaign in the lab, potentially with some peers. So.
Yes, well, hopefully not too much. But yeah, it's good to hear from other people that the lab is well run. But yeah, I think if you're going to do this, then you have to decide that you're going to dedicate a lot of resource to doing it, because it needs that to do it well. And unlike anything else in science, there's no point in doing it unless you're going to do it well and produce data that you're confident in and that you can defend to other people.
Yeah, because apart from the time, like doing these analyses also costs money. It's, we have to use super clean acids, concentrated acids, and you need to buy those supplies. These things cost money. And so you don't want to, do a rush job, get poor analyses that end up just being a waste of not only your precious time, but also a lot of money.
Yeah, and I think what a lot of people don't realize is just the amount of money that's spent just to keep the lab being there available for analyses. So running a clean lab of the sort that you need to do this type of analysis means thousands, tens of thousands of dollars worth of clean air filters that are continually operating just to push what is actually, in pretty much any part of the world, extremely dirty air. Even if you live in a place like Canada, where there's very little industrial pollution, at least in the west of Canada, there's a lot of dust in the atmosphere, just natural dust that you have to filter out. And having a filtration setup in your lab to take all that dust out of the air costs tens of thousands of dollars. And you've got to keep that running, and you've got to keep a positive pressure in your lab to keep all the dust out of the lab continuously. And so that's all the power commitment to doing that. And so you need pretty deep pockets to be able to keep a facility going that's ready and available to do this sort of work. You don't have a lab that you just sort of switch on and start operating to do the work and then just turn off and draw the curtains and walk away until the next analysis.
Yeah, no, for sure. And so now I wanted to sort of touch just on, the differences between colored stones or colored gemstones and diamonds, because we know that trace elements are used to try and do country of origin. They're not always successful, and they have the same problem as with diamonds in some cases, where there's a lot of overlap between different localities. And so, we've spoken about doing trace elements in diamonds in your lab, but your lab has also done some trace elements in rubies. And I was just wondering if you could speak a little bit about that.
Yes. So and a student, Mandy Krebs, who did a PhD in our lab, working with a number of people supplying gems, for instance, the Gemological Institute of America and what was True North Gems at the time, to supply rubies, where we were looking at trying to distinguish the place of origin for rubies, because particularly for coloured stones, the place of origin has a big impact on the price. People, for their own reasons, are willing to pay a lot more money for coloured stones, sapphires or rubies from a particular one place versus another. The price differential can be orders of magnitude different. But also from an ethical point of view as well, where people quite rightly might want to not purchase stones from mines or part of the world where people are being forced to mine those stones, or are being employed in really quite bad, abusive conditions. So there's lots of drivers for why you would want to determine the place of origin for either a coloured gem or even a diamond.
Yeah.
And so with the coloured stones, well, for rubies, life is a little easier in that it turns out that there's lots of trace contaminants, or lots of inclusions in rubies that actually give you quite large signals for some elements. So the analytical challenge for rubies, well, A, is similar in that they're very physically and chemically robust materials. So one of the few ways of accessing the interior or the geochemical signal of a ruby is, again, to use a laser. But there's far more of the trace elements of most trace elements in rubies than there are in diamonds. Sapphires are a different matter. So very pure sapphires actually have also vanishingly low levels of trace elements. And so Mandy's work on the rubies worked out pretty well. I think we extended the range of elements that we could analyze within rubies, and we did some of it by direct ablation and some of it by close cell ablation. I think there with the rubies, the measurements then are actually more straightforward to get the data. And now what's needed are some more sophisticated statistical approaches to take that to an identifying place of origin concept, which I think that, combined with the difference in physical characteristics of a lot of rubies in particular, makes that problem really quite tractable, because of the combination of characteristics of inclusion types, sizes, geometries in different ruby deposits around the world, and the fact that rubies form in a variety of geological environments that give you this nice spectrum of geochemical signals, both from an elemental point of view and from an isotopic point of view, that you can fingerprint the sort of source. You can see actually the fingerprint in the source rocks that the rubies are forming from in the isotopes, in the strontium and in the lead isotopes. In diamonds, it's a little bit more difficult, because there's really only two different source rocks, two major source rocks that diamonds occur in: eclogites and peridotite. So olivine-rich peridotite that comprises most of the mantle, and then eclogite, which is essentially subducted oceanic basalt. And even in those environments, the sources of the fluids might involve similar materials, subducted carbonates of one form or another. And so I think there are less parameters to play with that might contribute to giving you a different spectrum of elemental and isotopic signatures. So nonetheless, I mean, we did some initial tests during John McNeill's thesis, actually, which looked promising. It's just a numbers of samples issue, but we analysed some diamonds from the Northwest Territories, where, and again, it depends what statistical test you choose to make, but we felt the initial data set you could use to answer the question, what is the probability that this diamond came from this mine or this mine, that were relatively geographically close to each other. We felt we could answer that question with fairly high confidence with that data set. Now, that study needs to be expanded to many more different places around the world for that to be a really robust conclusion. But it was promising enough to give some hope that this might be possible. Certainly when it's come other things like diamond surface features and inclusion types and other parameters, then there is some hope that this might be possible. I don't think it's ever going to be something that you're going to do routinely, because you need to send the samples to a lab, a quite specialized lab. But I think there's some hope that in cases where there's a really important question to solve, is this parcel of diamonds from a particular place or not? What is the problem? You can never answer anything absolutely like that, but what is the probability that they're from this particular place? Then I think it offers some hope that we might be able to do that. But to do any of it, of course, you need the bigger global database to compare with. So
of course,
to build that database. And of course, one of the issues is that it's actually very difficult to get diamonds from some of these problem areas that people have identified in the past and that continue to crop up every now and again. Certain parts of the world where diamonds are either being mined illegally or under conditions that abuse human rights. It's actually very difficult to then get verifiable parcels of stones from those locations to work on for obvious reasons.
Yeah, so a lot more work to be done.
Yeah, that's right. Lots more. But the nice thing is that in doing that work for provenance work, that you would also generate a huge amount of interesting scientific data that should tell us a lot about how diamonds form, what the different fluid sources are, etc., in different parts of the world, whether there are these globally similar processes and how those processes might differ in detail in different locations.
Just to go back and add, because you mentioned that the rubies have such a higher concentration of these trace elements than the diamonds. Just could you quantify that to say like how much higher they are?
Yeah, it sort of depends on the element, but so the rubies can have maybe 1,000 times higher concentrations of some of these elements than gem diamonds, even more, maybe 10 to the 4, 10 to the 5 times more of certain elements, especially elements like aluminium. Ruby is essentially dominated by the element aluminium, and elements that are geochemically similar to aluminium, like gallium, etc., then have much higher concentrations than a gem quality diamond. Yeah, probably 10 to the 4 times concentrations, which then actually makes those particular elements, you can measure those fairly straightforwardly, even with a direct laser ablation analysis. But again, with the rubies, the issue always comes back to having a good, reliable, homogeneous ruby standard, and we're not there yet either. So some effort is being put into that, and some progress is being made in generating corundum standards, which is a little bit easier to do and synthesize than it seems anyway, than homogeneous diamond standards at the moment.
Okay, well, this is a great conversation. So thank you very much, Graham.